Can everyone hear me? Is this working? Okay, good. So that's a lot of places, hey? But it all started here, so I get to say a personal thing before I do technical stuff. This was a long time ago when computer monitors were very fat and I was very thin, okay? And so, and like a lot of people like Vikosi and Shakir and Banji, at the time we were very excited about doing research, but you had to leave. Right? You couldn't be here. You had to do your masters and maybe, or your honors, maybe your masters, then you had to go overseas because that was where it was at. And there's a long tradition of that. I had to point this out because I think Jan mentioned Seymour Papert, who wrote this book, Perceptrons. Seymour Papert did his PhD at WITS, actually. He's a WITS graduate. So we have a long tradition of sending very smart people overseas, and then that's what you did, right? But one of the things that's wonderful about this meeting is that that's not true anymore. Okay? I'm no longer thin, monitors are no longer fat, and you don't have to go overseas. There's a real community here making stuff happen, doing cutting-edge research, and that's super cool. And that's down to you guys, so congrats. Okay, nostalgia over. So Benji and Vikosi talked about reinforcement learning. They talked about agents that interact with the world, and they can take actions, and they receive states, and they receive little rewards which tell them what to do. So inside this diagram is like almost, not quite, but almost the totality of the AI problem. Right, so there's a lot of stuff happening in this diagram. And what we've shown you so far, both the agent and the world are kind of little and fairly simple. Right, so you get problems that look like this. They're sort of grid-worldy. They've got a small, finite number of things you can do. But really, the world looks more like this. It's much more complicated. There's a lot of stuff going on, and it's very high-dimensional and continuous, both in the action space and in the sensing space, right? So if we're going to solve the whole AI problem, which is what we're all in this to do, right? All of us? Yes. If we're going to solve the whole AI problem, then we need to take seriously the fact that the agents that we're using are actually complicated things. So we can't do things in real life like learn discrete value functions. Okay, these things are just tables. You just put a value in a table, and that's an easy thing to represent. Instead, we have much more complicated scenarios where we have to represent these things that are functions of real valued numbers, or vectors of real valued numbers. So instead of these kinds of nice things that are kind of easy to represent, you get these kinds of things which are complicated and have lots of bumps, and might have lots and lots of important things happening in a small space, and then not much important happening in another space. So we might need real valued value functions. We might need real valued policies, right? That's state and action for the policies. And we might need real valued environmental models. And the key issues, if we're to learn this, one of them is how do you represent these things at all? But the kind of key issue that you need to keep in mind when you think about these are that there are, in a real valued situation, there are uncountably infinitely many states. Because that has some consequences. One consequence is you can never expect to see the same state again. But you can't say, I've encountered a state, something happened, I've changed the value of that state, and then later on I'll get some more data about that particular state. That doesn't happen. You see states that are similar to each other, but you often don't see exactly the same one again. So imagine if you have an agent that is something like video input, you're not going to get the same frame. It's just never going to happen. So you have to generalize. You have to say, this frame of video input is very close to this frame, and therefore the values, or the model, or the policy should be very similar in that situation. You have to generalize across these things, right? And you want to be able to do this compactly, so that even though there are infinitely many states, and possibly infinitely many actions, you are able to represent that in a small finite thing you can put in your computer. So how do we do this? How do we think about representing these real valued functions and learning using them? And it's exactly as we've seen before, which is to say that you are going to represent some function, could be a value function, it could be a model, could be a policy, f of x, as a parameterized thing. Okay, so it's got, so f has some parameters, it's a function of x, which in our case could be states or could be actions or whatever, depending on what we want to learn. It's going to have some parameter vector w. And then you're going to write down an objective function. And you're going to optimize for that objective function. And typically, you're going to optimize with gradient descent. Not always, but typically, right? So any time, I did a lot of applied math when I was at WITS, and it was great. At the time, I thought it was obnoxious, but actually it turned out to be really useful. Anytime you can take a problem and you can turn it into this sort of form, then you have a wealth of mathematical tools that you can use. Okay, so let's talk about the three things that we might wish to approximate. We might wish to approximate a value function, a policy, or a model. So I'm going to go through each of these, maybe in a bit less detail every time. And I'm going to talk about the simplest case, and then maybe in a little bit of mathematical detail, and then I'm just going to show you what the more complicated cases look like, because no one's got time for all that math. Right? So let's talk about value functions. So what is the function that we want to represent for a value function? You've got your Q function, which Benji and Vikosi have been talking about. It's a function of states and actions, and we're going to add a parameter vector to it, W. And what this thing does is it maps from Rn, or some large vector, to R. So it gives you a real valued output for if you choose a state and an action. So your state could be a vector of real numbers, your action could be a vector of real numbers, and it's going to output a single real number that says this is the expected return from this state if you took that action. So what might our objective function look like? Well, what does our data look like, first of all? Our data looks like this. You run around in the world, okay, you act, and stuff happens. And you don't have a model of the world, you're just acting and seeing what happens. And you get collections of these little transition tuples. So you get a whole trajectory, and each trajectory looks like this. You were in some state at time I, you took some action at time I, you received some reward at time I, and then you landed up in a state at time I plus 1, and then you took an action at time I plus 1. Okay, so this looks familiar from the previous lecture because that's Belsasa. So that's what your data looks like. And then you might have noticed that there's this quantity central to all of reinforcement learning called the temporal difference error. Okay? So that is a measure of how good your value function is, just looking at this state and the next state. So we can write down an expression that says, let's minimize the sum over that trajectory of squared temporal difference error. So minimize, choosing W, you get to choose your weights. Minimize your estimate for Q at time I minus reward plus gamma Q at time I plus 1. And we square that thing because we don't want errors to cancel out. So this looks familiar if you've done regression. You do least squares regression. You get a sum squared error. This is a sum squared error, but the error is a temporal difference error. It's not a prediction error. Okay. And so what you can do is if you have this thing, you can take its gradient, right, because it's a piece of math, and we know how to take the gradients of pieces of math because we did our mandatory math courses in undergrad. And we can try and descend it, or we can do something with the optimization here. So given a function approximation, compute the gradient and descend it. Now, I haven't talked about the form of this Q yet, and the form of this Q is going to tell you what that derivative looks like. So how should we construct Q? And that turns out to be, or how should we approximate Q? And that turns out to be like the dominant question in reinforcement learning, right? The whole deep network revolution showed us that our algorithms are actually fine. Really what we've been missing for decades, because the algorithms used in all of the latest exciting things are actually not that different from what they were a decade or 2 decades ago. It turns out that representing things appropriately, having this powerful function approximator, was the thing that we were missing. So what's the simplest thing you could do, because you should always start with the simplest thing you could do, is you can write down a linear function. So you've got some weights, and you've got some basis functions, phi, and we'll talk about what they might be in a little bit. You've got n of them, and you want to represent your function as a linear combination of those basis functions. Okay, so you've got phi 1 to phi n, and you're going to write q. This little hat means an approximation to q. It's not the real q. We might not even be able to ever represent the real q, but our approximation to q is w dot that vector of basis functions, which is the same thing as summing over all the basis functions, pull out the ith weight, multiply it by a basis function. Okay. Now this is actually quite useful because these basis functions can be anything you want. As long as they're only functions of states and actions. They can be arbitrarily complicated, right? You can spend years writing what those basis functions should be, but the form of the derivative is very simple. So let's think about what they could be. What is the simplest way that you might wish to approximate a function? Okay, so if we think back to first year math, we think about Taylor series, right? What's the 0th order Taylor series, or the first order Taylor series of a function? It would have basis functions 1, x, and y. Sorry, actually, if you just use the state variables, you could get 1x and y. So you could imagine weight W0 times 1 plus weight W1 times x plus weight W2 times y, and that's a function of x and y. Right? And it's got 3 parameters, and you could optimize them. Or you could do a Taylor expansion. You could say, let's start with a first-order polynomial over x and y. If x and y were your state variables, you would have basis functions 1, basis function x, basis function y, basis functions x times y. Okay, so that's 4 basis functions that you might wish to use. And then you could do that expansion a bit further and say, let's do a second-order Taylor series. So 1, x, y, x squared, y squared, x squared y, y squared x squared, y squared. Okay. And this is like a Taylor expansion of a function around a point. Okay. So that's boring, because it's kind of boring because it takes a lot of energy to write these things out. You see that it explodes pretty fast. First order has 4, second order has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10-ish, somewhere in there. I lost track. Has a bunch of them, right? But what do we know about Taylor series expansions? What can you represent with a Taylor series expansion? Pretty much anything. If you have enough basis functions, right? If you have enough of these terms, you can represent anything with a linear thing, right? So, okay, so what's another thing that you could do? You could do a Fourier series expansion. So Taylor series expansions are good at representing some types of functions and bad at representing other types of functions. A Fourier series is good at representing smooth functions. Okay, so you could imagine saying, okay, let's take x and y and write down a set of basis functions. The first one is 1. The second one is cosine pi times x. The third is cosine pi times y. The fourth is cosine pi times x plus y. And if you look at what those basis functions look like, for what you do is you enumerate coefficients for x and y. And the coefficients tell you the frequency with which the function changes along that dimension. So if you have a coefficient that's 1 times x and 0 times y, it changes in x, but it doesn't change in y. If you have the same thing in 0 for x and 1 for y, it changes in changes in y, but not in x. And if you had something like 2 times x and 5 times y, it changes in a kind of wiggly way in the combination of these two things. Okay. So we have a set of powerful tools where if we can do this kind of linear expansion easily, then we can do linear value function approximation. So what does the algorithm look like? Okay, so let's do the stochastic gradient descent thing. So that means that instead of collecting up all your data and trying to minimize y over all of it, what we're going to do is we're going to get one transition tuple in. We're going to compute the gradient with respect to that transition tuple, gradient with respect to w from that transition tuple. We're going to take a small step, and then we're going to take another action. Okay. We're going to descend the gradient a little bit, and then we're going to say that QSA is equal to w.phi SA. So we've got our basis functions, which we hand designed, and we're going to write down our approximation of Q that way. And then we can just substitute into the objective function, and we see that you could minimize W by summing. This is just the TD error. But you've substituted W.phi for Q. Okay, on both sides, because there's a Q at SI and a Q at SI plus 1. And then we want to take that thing and we want to calculate its gradient. So we take it and we do the derivative of it. And if we look at the partial derivative for each weight, so we have to calculate a derivative for each weight. That's how much each weight changes. And if we do that partial thing, this looks complicated, but this is just a function of W squared. So we use the, what's the name of the rule? Chain rule, right, yes. So you bring that 2 down and you write this thing again, and then you take the derivative of the thing inside here with respect to W. Now we're cheating a bit. We're pretending that the second W is fixed. So this is like a target. This is the thing we get to change. So when we do the derivative, we get this very simple thing. It's the jth basis function. Okay. All right, so for each individual state, so this is a sum over all the states in the trajectory. For each individual state, that's the trajectory, that's the piece of gradient for that individual state that arrived. Right? This is a sum for I equals 0 to n. This is just the ith term. Okay? And then we make a step in that direction. We say that the jth element of w at time I plus 1 is the jth element of w at time I plus alpha. This is a gradient descent step. And then that is the TD error, and that is the derivative of the function. And because things are linear, this is very easy to compute, right? That taking the derivative of that TD error with respect to W is really easy for a linear function. It's one of its advantages. We can rewrite this thing in a very simple form. W to I plus 1 is WI plus alpha delta phi. Alpha is your learning rate, delta is your TD error, and phi is your derivative of your function approximator with respect to W. Yes? W on the right-hand side is at st plus 1 is a constant. No, so this j is the index of the jth element of that vector, not the weighted at time t. So there's two indices going on. One index is the time, so you've got you've got a bunch of samples, and so you could say the state at time I, and the other index is j, which is you've got a vector of w's, and I just want to look at the partial derivative of one of them. Yes, w is a vector. Yeah, and I'm pulling out the partial derivative of just one. So the whole thing is a grad, but I've just pulled out one of the elements. So, does that make sense? Okay, and so this thing is TD error, this delta is TD error. So you write a piece of code, takes a step, computes the TD error, and you say W is W plus alpha delta phi. Benjamin Vicosi talked about TD lambda, and what TD lambda does is this TD error, instead of being a one-step TD error, is a weighted sum of TD errors over time, weighted geometrically by lambda. So you can do the same math by just substituting into that expression, taking the derivative and doing the whole thing. Okay, it's kind of boring. We're not going to do it here, but I'm just going to point out that the weights used to be alpha, the weights that used to be alpha delta phi, right? That's one basis function's derivative, becomes alpha delta E, where E is your vector of eligibility traces. And how does that vector evolve? At time 0 in your at the first time step in your episode, it should be 0 everywhere. And then every time you take a step, you multiply what it used to be by gamma lambda, and then you add on phi. So you can see that if lambda was 0, this term would never ever be in the expression, and alpha delta E would reduce to alpha delta phi. But when it is in the expression, you get a sum of these previous phi's, and they're discounted by geometrically by lambda. So the further they are backwards in time, they're t steps back in time, they'll be multiplied by lambda gamma to the power of t. So they'll be shrunk backwards. Okay, so this is called Sasa lambda, and it's actually pretty simple. The math is ugly, but when you get to the end of the math, then things are simple, which is the way we like it to be. And you can solve some relatively simple problems with it. So this is the Acrobat problem. Here you've got a sort of pair of arms linked to a fixed joint in the ceiling. This is like you're hanging off the ceiling, but you can only actuate the waist. Okay, so you can't actuate with your wrists. You can only swing your waist. I don't know if as kids you used to hang off door frames. I used to do that. And you'd kind of swing your legs to try and gain momentum to get up above, and the goal is to get up above this red line. So we can run TD lambda, Sasa lambda in real time, and we can get learning behavior like this. So this is the first episode. It's kind of thrashing around, looking a bit random. This is a four-dimensional problem. Okay, so the state is theta for the two joints and theta prime for the two joints. And the actions are you can add torque in either direction or you can wait. And so what's happening here is the exploration is driving the agent away from states it's been in before, which didn't get it a reward, towards states that might give it a reward in the future. Eventually, it's going to figure something out. Nearly. Life's tough as a reinforcement learning agent. Okay, there we go. So that was the end of the first episode. So the second episode you'll see is markedly better. Kind of has some feeling for what it's doing. Not as much as you'd like, though. There we go, okay. I think there are 6 episodes in total that we're visualizing here. Getting better and better at this, right? At some point, I'm going to borrow someone's small child and hang them from a ceiling and see how long it takes them to do this, right? 6 episodes might be close to human performance. Okay. And so the learning curve, Benji and Vikosi showed you a learning curve that goes up, that's return over time. I've cheated a bit and just said number of steps, so it goes down. Those happen to be minus the other in this case, so just flip it in your head if you're confused. And you can see that, as Benji said, there's a lot of slow learning at the beginning, thrashes around, and then over time kind of gets better and better. In this case, on the order of 10 episodes, it's as good as it's going to get. Okay. So actually, that's a really good class of general purpose reinforcement learning algorithms, right? With this nice, simple linear function approximator. In fact, it's so simple that you might have a question. You might say, you know, I see that we calculated the gradient, but linear things, we should be able to do something a bit better than that. And in fact, in general, for a linear setting, you don't have to descend the gradient. You can just go straight to the solution. Right? There's a closed form solution for the W minimizing that expression. So if we take our objective function and we notice that this error has a bowl shape, okay, it's a quadratic error, so it's got only one minimum, and we just take its derivative and we set it to 0, then we can solve the thing. Okay, so if we take the derivative of this thing, of that thing, which is this piece of math, this is the TD error, this is some extra stuff, and we set it to 0, and then we pull W outside, we get this slightly ugly equation. Don't worry about it. The point is it can be written like this. Okay, so where A is this trace matrix, that's TD error multiplied by the derivative of the function, and B, sorry, not TD error, it's the difference between the two feature sets, basis function sets, and B is the reward times the basis functions. Okay, and if you invert A, you can solve for W. And you solve for W in a closed form. Now, you can't do this per step because it's expensive, and also the matrix is not going to be invertible. But if you have a batch of data, if you have like 100 data points, you could collect up this A and this B function, and then you could just solve for the value function. And that works when you can invert that matrix, when that inversion is stable, which is often not the case. And when the matrix has sufficient rank and other technical things like that. You can do the same thing for TD lambda. We're not going to talk about it now, but all you do is and so you should try it at home. But all you need to do is, when you write down that objective function, you remove the sample, this thing, and you replace a complex lambda multiplied thing. And then you do some math, and you get a similar sort of thing, except the equation for updating A and B is a little more complicated. Okay, but it does this sort of trace thing. So why would we not always do that? Okay, one inversion always solves for W. That seems like a nice thing to do. And there's a couple of reasons. One of them is you may need many features, many thousands of features, and so then you get into this regime where you're trying to invert a 1,000 by 1,000 matrix. And that's okay if you can build that matrix such that it has rank 1,000. But often that's not the case. So then you have to you have to regularize that thing, and it starts to sort of get ugly. Sometimes also the behavior is unstable. So every time you invert that matrix, you completely change the policy. You completely change everything. So there is an algorithm called least squares policy iteration, which requires you to compute A, invert it, and then find the policy that maximizes A in your queue for every state. But then you have to recompute A again. Every time the policy changes, you have to recompute that whole big thing, so you need to store a bunch of stuff in memory, and overall it's a drag. It is the best performing algorithm if you can do that inversion and you can store sufficient stuff. Okay, so that all sounds wonderful. So linear methods sound great. We can write closed form solutions for them. We can write gradient descent solutions for them. And we know that we can represent anything. So this property of them being complete is nice, right? People often talk about neural nets being complete. So is a Taylor series. So is a Fourier basis. And they have this nice property that there's a unique minimum. So there's no local optima. And they're super easy to use. because I've just written down the thing for you. There's a bunch of pieces of code that do that on the net, and you just drop in a basis function. Okay, but they don't scale. They're fatally flawed. Okay, and where does the fatal flaw come from? Yes, so here's a question. How many Taylor series terms do you need for an n-dimensional, for an order n Taylor expansion when you have d variables? Okay, so if you have one dimension, you just need n plus 1, right? If you want to do like a second order polynomial, you just do 1 and x squared. So that's 2 plus 1, that's 3. Okay, what happens if you have x and y, and you write that down? You'll see that you need roughly the squared of the order number of basis functions. More generally, you need n plus 1, n is the order, to the power of d, okay, to do a complete Taylor or Fourier series expansion of a function. This is terrible, right? You don't ever want to have to do this because exponents in the number of basis functions that you're using are unhappy things. Okay, it blows up ridiculously fast. So you can use something like a Taylor series or a Fourier series if you have about 7 or less dimensions in your data. After that, it starts to get unwieldy. It starts not being able to fit in memory. Even though this was the case when I was at WITS, and a lot of things have changed since then, but it's still way too easy to blow up if you insist on doing a linear function approximator. Okay. So that has motivated people using more complex and more interesting function approximators for value functions, and they've been doing it for a very long time. In particular, they've been using neural nets for a long time. So this, circa 1992 to 1995, was the AlphaGo of its day. Not as impressive as AlphaGo, but still pretty cool. So Jerry Tesauro wrote a program called TDGammon that learned to play backgammon by playing itself. So on the order of 1.5 million games, and it used a value function just like I've talked to you about, using an algorithm just like we've spoken about, except that that derivative term is a bit more complicated. Okay, you have to take the derivative of a neural net. So that's ugly, so what you do is you look at the TD error, and you do backpropagation to minimize that TD error. So just the algorithms that we've already been talking about, instead of minimizing classification error or regression error, you're minimizing TD error. And he used TD lambda. And what was really cool about this is that he was able to beat the best players in the world. And actually, that TDGammon changed the way that the best players thought about some stuff. So like most games, there's a body of theory about how you play this game. In backgammon, there's like books of openings that you use. And there were substantial major theories about how you played the opening that changed because TDGammon didn't play that way and beat everybody. And so people reevaluated the theoretical knowledge that they'd built after having played and lost to this thing repeatedly. So this was really exciting when this happened. This was like an early win for RL and really a big deal. But TDGammon is orders of magnitude simpler than something like Go. Oh, that's a good question. I have not asked. I assume not, actually, because, well, I mean, 1992 to 1995 was a long time ago, so I imagine you could like multiply by 10 the number of games and stuff like that. They're not going to be able to keep up. It's too simple a game, fundamentally. It's a hard game for a person to play, but fundamentally it's not that. It might be harder than chess for computers, but it's much easier than Go. So more recently, you may have all seen this very exciting arcade learning environment thing. So what the arcade learning environment is it is 49 games from an Atari gaming console. Someone got the code to that. Actually, Mark Bellamar got the code to that, and he wrote an emulator for all 49 games. And he wrote a bunch of surround code that allows you to access the state of the game, to access the pixels on the screen, and to be able to actuate the joystick. Okay, so you could do reinforcement learning over these 49 games. And what was super exciting and very challenging about this benchmark, which was released only in 2013, is that you are supposed to learn these games by direct visual observation. So you don't get a little small 5-dimensional vector that describes your state. Instead, you get, I think it's 86 by 86 pixel image that describes the state of the screen. And usually what you do is you take a couple of screens of history. So I think they took 4 screens of history. So it's 4 times 86 times 86 is the size of your input. And at the time this came out, everyone thought, wow, it's going to take decades to be able to solve this, right? This is going to take forever. But just 2 years later, with the advent of an algorithm called DeepQ Networks, developed at DeepMind, actually, right before it was acquired by Google, which may or may not be a coincidence, okay, built a DeepQ network that started with, so they were grayscale, those images, they were grayscaled, 4 images of history, all collected, and then a sequence of convolutional layers, all the way out to predict the Q value of one of the finite number of actions available to the agent. And there was a lot of complexity in this, okay? So they had to gather large numbers of training data. They trained it in a batch. They didn't do stochastic gradient descent. They had batches, and the batches were like hundreds of thousands or millions of frames. And they were training learning over these batches, and they were replaying the batches. There was a lot of stuff going on. But the point is that they were able to beat or they were able to do pretty well on almost all of those 49 games using the same neural network architecture and the same learning algorithm. This is a major advance in AI, right? Because it's not that you've engineered an algorithm to solve a problem. It's that you have one algorithm that is generalizable across 49 problems of similar type. Okay, and it produces behavior like this. So this is Breakout, is it? I think it's Breakout, which is an old Atari game. Hey, right, yeah, there we go. Okay, good. So this is after 10 minutes of training, where you can see that occasionally it loses, right? There's some unfortunate things in the beginning. Okay, but after 120 minutes of training, we're exceeding expert level at Breakout. That is directly from pixels. Yes? That's a good question. Actually, I think it's 120 minutes crunching GPUs. I think it's not. I think it's millions of frames. So like all deep nets, you know, these are very powerful representations, but they're not data efficient necessarily. That doesn't matter though, because this is still. That doesn't matter though, because this is still so far beyond what people could do before that. Being able to do it in a million games is a gargantuan win. And when I say they beat expert performance, what I mean is that they hired a dude who was really good at Atari games, and they brought him in to play Atari, and they recorded his performance. So this graph in the science paper is super cool. So this line over here is human level performance. All the games below this, they're not as good as people. The x-axis here is percentage of human performance. And they said, if you're within 75% of the performance of the expert that we hired for being good at this, then you're at sort of human level performance. Okay, so 100 is human level performance, or 75-ish, that's about where we are to exceed human level performance. Sometimes human level performance is just blown past by this sort of thing, right? And sometimes, for some classes of games, we're not able to do it yet. This was a while ago. There has been an absolute feeding frenzy of trying to improve performance on this thing. So this graph is 2 years out of date, is like 10 iterations out of date, probably. Yes? Yes. So it's not the same network. It's the same network architecture. So it has the same hyperparameters and the same initiation state, but then it learns to solve each individual game. Yep. Yes, if it was the same network, that would be wildly surprising, because it would be cool, but it would be wildly surprising. Yes? So that is a very interesting question and the subject of a lot of research. That game is called Montezuma's Revenge. I don't know, you all are too young to have played Montezuma's Revenge, but it's like this sort of quest game where there are these screens and you have to kind of jump up and go up ladders and down ladders, and it has this characteristic where, you know, there'll be a key on the third screen 2 things down that you need to open up a door 5 things down and to the bottom. And so you have to have very deliberative planning-like behavior in Monty's Revenge. You have to say, okay, now I'm going to go get the green key. And therefore, I'm going to do this whole long thing and get the green key. all the while jumping over the little snakes and not falling down the pits and not dying. So my opinion on why this is not working for Monty's Revenge is that the solution is very narrow, right? If you're off by a little bit on either side, you fall into a pit. And also it has these very long sub-goal things where you chase a sub-goal for a very long time. And the reasoning about which sub-goal to chase is quite complicated, right? You need the green key to open the green door. And that's, like, this is learning directly from pixels, right? So there is something that says this is more of a, what this is good for is more of a reactive Twitch game type situation where you see something, you switch off your prefrontal cortex and you just react. And most games are like that, right? But there isn't necessarily deliberation. Okay. So the other thing that we could approximate with a function approximator, we've talked about value function approximation. We could also approximate a policy. Okay, so Benjamin Vicosi talked about this a little bit. So what you do is you have your policy, which is a function of states and actions, and a parameter. We're going to call this one theta instead of w because it's just conventional to do that. And what that does is it maps your real valued vector of states and your real valued vector of actions to a distribution. Okay, so this is a probability density function. It says, for this action, this is the probability that you should execute it. And the way that you're going to choose the action is you're going to sample it from that distribution. Because we need a stochastic distribution. So why might we do this? Well, there's a couple of major reasons. One major reason is that policies are typically much simpler than value functions. Okay, so the value function for some games is really complicated, but the policies like go left when you see there's an alien in front of you and the rest of the time shoot. Right? So you can actually write down very simple policies that solve most problems. If you can avoid the value function, then you might be able to optimize for the much simpler thing you're looking for anyway. The other thing is that it's much easier to inject structure into the policy. So imagine that you're doing learning on a robot. Okay? This is one of the major applications of this sort of thing. You don't want completely general functions of states to actions. Okay? Because when you're on a robot and you're like swinging wildly in your actions, it's very easy to break your robot. In fact, maybe you know that the behavior that you're looking for is quite smooth, or it should never exceed a particular velocity limit, or it should always move towards some particular location no matter what. And any of that structure is very easy to include in a policy search algorithm, so that you can guarantee that something horrible doesn't happen. Okay, so imagine that you're deploying an HIV and AIDS treatment. You can produce a class of HIV and AIDS treatments that your physicians all agree are not crazy. Nothing totally random is going to happen. You just might be able to optimize over them. Right? And so therefore, we're living in a safe family of policies. It's okay to do learning in that family because no one of them is so bad that it's just going to like wipe out everyone in the ward. Okay, so that's why you would want to do that. And then we should ask, what does your objective function look like? And that sort of depends. Right? So what happens, well, generally speaking, your objective function is just that you want to maximize reward given theta, right? So you want to choose theta that maximizes reward over or return, sorry, the sum of rewards over your episode. So how might you write that down? Well, there's a couple of issues. What happens if you can't differentiate pi? Okay, we've all talked about policy gradient. If you can differentiate pi, you could imagine taking the gradient and descending it. If you can't differentiate pi, then it's kind of not clear what you would do. And if you've taken an optimization course, one of the things you do in a situation like that is you have your sort of current best theta, you sample some thetas around it, and you kind of approximate a gradient. Right? You sort of build a local estimate of the gradient, and you ascend that thing. So hill climbing is one such thing. If you're on an optimization surface, you kind of sample around, and you try and go up the hill. Right? So sample some theta values near your current best theta, adjust your current best theta to sort of the highest one, or some combination of them that's weighted by reward. So here's an example of policy search, which I've always really liked. This is quite old. This is from 2004. So do you all know about RoboCup? This was this competition where robots play soccer, and it used to happen with these tiny little dogs, these Sony Ibos. And one of the curses of RoboCup as an AI platform, it was a great AI platform, it was a great kind of thing for everyone to do, but one of the problems was that it was always won by the people who could walk the best. Right? Your AI algorithm didn't matter. If you could walk in this kind of weird dog faster than the other guy, then you won. And so there were armies of graduate students deployed to hand engineer gates. So this went on for some time. There were some times where like universities had like upwards of 10 graduate students working on optimization by graduate student gates. Okay. And so Nate Cole and Peter Stone said, well, we know a lot about gates. We can write down a gate program, right? If you're one of these dogs, you move like this. Okay, so we can say, well, there's an ellipse. And maybe we don't know how far the bottom part of that ellipse should be, or how fast you should move when you're on the ellipse, or how much angle you should have, but we can write a program that generates an ellipse, and that program, in this case, had 12 parameters. Okay, so there are things like the front locus, height, x position, y position, the rear locus, the locus length, these sorts of things. And now we're going to optimize by sampling values for that thing, and then moving in the direction of the averaged best thing. So on the top is the best gate that was available at the time. And it works, but it's not amazing. This is the gate after, I think it's 3 or 4 hours of optimization on a robot. So what's cool about that is that single algorithm in the space of a couple of hours beat armies of graduate students. Right? This was the best available gate that you could get, and therefore they won RoboCup a bunch of times. I'm actually going to skip this one because we don't have a ton of time. If you can differentiate the policy objective function, what you should do is you should just compute the gradient and ascend or descend it, depending on whether you're maximizing return or minimizing cost. So you want to take the derivative of return, that's the discounted sum of rewards, by theta, which is the parameters in your policy. Okay. So there is an algorithm called reinforce. I'm not going to explain it now because it's in your tutorial, and Stefan and his group did an amazing job of writing it all up. But what it amounts to is one way to approximate this gradient is to say the gradient of theta t is alpha, that's your learning rate, times r, that's the reward that you receive, times this ratio. This is the derivative of your policy with respect to theta over the policy. Okay. This doesn't require any models. It doesn't require anything very complicated. It doesn't require a value function. It just says, gather up some rewards, go along, compute this gradient for each trajectory, and descend the gradient. And you will all be implementing that this afternoon. It's going to be great. Okay, so there is a slightly more general type of policy gradient algorithm. Oh, are we doing okay? Everything's good? Okay. Called the policy gradient theorem, and that says that partial derivative of r with respect to an individual theta works out to this equation here. So this is your distribution over states that a particular policy implies. And then this is summing over actions, the derivative of the policy by theta times this thing over here. And that's magic because this thing over here is a Q function. Okay, so it turns out that in one of the most popular policy search algorithms, you actually need a Q function to estimate your gradient. So you can bring in all of the previous theory, drop a Q function in there, and use it. And that might seem obnoxious because you've got to estimate a Q function again, but this theorem actually tells you that this Q function should be linear in the derivatives of this policy. So you can actually construct a very sparse Q function that has only as many parameters as your policy has parameters. Okay, it's a very sparse thing. To support the gradient, you need a small number of things. So you don't have to engineer the function approximator for Q. You engineer it for pi, and then you can automatically construct the linear basis functions that support your policy. And then you can do Q learning. So let's talk about a recent application of this using a deep net directly to robot sensory motor action. So this paper is from Sergey Levine's group in 2016, or Peter Beal and Sergey Levine's group in 2016. And they're learning a sequence of visual motor tasks like putting a cube in, picking up a cube and putting it inside one of those little puzzles that has holes for the cube. Okay, and using a hammer to sort of catch a peg. And the way that they're doing it is their input is visual data that the robot perceives directly, right? So this is an RGB image of the scene, and it goes through a bunch of convolutional layers. And then at some point, you include the joints of the robot in the feature set, and then you do a little bit more deep net stuff, and your output is motor talks. So you're going directly from pixels, that the robot is observing to how to actuate its motors. Right? There's nothing in between. There's no anything other than that. Now, the solution was quite elaborate. There's a lot of stuff going on. In particular, there was a bunch of pre-training to predict the pose of objects. Okay, so what they would do is, without using the robot, they would take pictures, they would hand label the poses, say this object is over there, this object is over there, and then train a deep net to predict those poses, and then use those features to kind of prime the deep net. Okay, because this deep net had 92,000 parameters. Okay, so how many samples do you need to get 92,000 parameters? On the order of 92,000 samples, and that's eons in a robot. Okay. So they kind of pre-primed the thing. And so this is an example of some of the learned visual motor policies that they were able to extract.
Here the robot inserts a block into a shape-sorting cube.
Gosh, hold on. I'm just going to silence that because no one wants to listen to the random... Right, so that's directly from visual data to motors in the robot. And you can move around. The visual test is they move around the position of the thing. They change stuff in the environment, and it hasn't learned a very specific movement motion. It's learned to actually bring the arm towards the position, put it in. So here they've changed where the robot is grasping the hammer, and no matter where the robot grasps it, visually it's able to adjust and be able to get the hammer so that it sort of pulls underneath a peg. So that was also a very substantial breakthrough in reinforcement learning, because before that, what we had to do if we were learning policies on robots is we had to construct quite limited policies, and then we would use them to do policy search, right? So we would really restrict the number of parameters in the policies in order to be able to do stuff in real time. And this has shown that you can actually get rid of a lot of that pre-processing and directly learn in sensory motor space. The third class of thing that we might be able to learn is a model. Okay, so we might be able to learn that transition function, okay, how the world works. Okay, so what the form of that is that it's a probability distribution over S plus 1, given Si and Ai and W. So if you were in some state at time I, and you took an action at time I, and you had some parameters, then you would predict a probability distribution over states at time I plus 1. Because the world is stochastic, so we can't just predict state I plus 1. There might be more than one that you land up with. And now, why might we wish to learn a model? We might wish to learn a model because real-life experience is complicated and expensive. Okay, if you have a robot and it bashes its head against the wall, it should learn that bashing its head against the wall, no matter what else happens in the world, is not a good thing to do, and it might learn a little predictor that says, generally when you're near the wall and you run towards it, you smash, no matter what you see. Right? It shouldn't have to repeatedly execute that to be able to pick up these complicated and dangerous and unhappy things. And if you have this model, what you can do is you can run reinforcement learning in your head and not have to actually go out and execute stuff in the world. Okay. So what might the objective function look like in this case? Well, again, you have samples of this form: state, action, reward, state, action. And generally speaking, what you want to do is you want to write down a likelihood function. How likely was this state I plus 1 given this state I and this action I? You want to find the predictive model that would have that would have been most likely to predict what actually happened. And so generally you can write down something like this. Now this is cheating for a reason I'll go into in a second, but often you can write a maximum likelihood is pick the parameters that maximizes the product of these probability densities. It's cheating because in order to do that, you have to assume that the samples are independent. Which they are totally not, right? Like trajectories are the exact opposite of independent samples, okay? Because they're very dependent on each other. State I and state I plus 1 are in fact completely dependent on each other. Okay? But if we don't make that assumption, then we don't get a closed form solution to the likelihood. So you can choose to do one of two things: make an incorrect assumption and just roll with it, or try and write down something that's not quite that's more principled, but now suddenly you have an expensive estimation procedure. You can't write down a closed form. Okay. So the procedure, once you've learned this model, is to say, get some transition data from the real world, learn a model that uses that transition data, run reinforcement learning on samples from that model in your head, generate samples from that model until you've converged, and then go out and get some more data. Okay. And this has some major advantages, right? In principle, this is the fastest thing you could do. Why? Because this part, learning a model, is a supervised learning problem. And supervised learning is just easier than reinforcement learning. Okay, it's an easier problem. Therefore, we can put supervised learning inside the loop, and we can use supervised learning to learn a model of the environment, and then we can do RL with as many samples as we like inside our own head. That's not a big deal. The unfortunate fact, though, is that people thought that this was obviously the right thing to do, especially in robotics, for at least from when I started thinking about reinforcement learning in robotics, which is about 2002, at least for a decade after that, and they tried and tried and tried, and it never worked. Right? It really, really, really never worked for a very long time. And why did it never work? It never worked because you believe this model. You run reinforcement learning on a model that's in your head, but all learning models are wrong because they're just models. And so the policy that you learn would overfit to the model, and it would do stupid stuff. It would be brittle. And when it got to some slight difference in the world, it would run off the tracks. So there was a breakthrough in about 2011 by Mark, who's sitting over here somewhere. Mark, where are you? There he is, okay. So Mark solved this problem basically for the entire reinforcement learning community by pointing out that since your model is never exactly right, and you can't plan as if your predictions are correct, what should you do instead? Okay, and if you've paid attention to the probabilistic reasoning thing that you've been hearing, what you should do instead is think about your distribution over models. Don't believe your models, but actually take into account and be serious about the uncertainty about what your model is predicting. So don't maximize your return over the most likely model. Maximize return integrated over the distribution over models. Okay. This is like Bayesian policy search. And this was a serious breakthrough, which led to this cool video. So this is a cart pole. So there's a little cart there that has a little motor that controls. No, there's no motor in here. There's just a motor that moves the cart up and down, and it has an arm that's kind of hanging. And it's got to move up and down, and it's trying to bring the arm vertical. So this is the entire learning procedure from scratch. Okay, this is episode 1. Just doing sort of random things. And that's Mark moving it back at the end of episode 1. This is episode 2. So in between these episodes, it's doing an optimization procedure where it optimizes the policy with respect to the distribution of models that it thinks might be true. It's gathering up the data that it experiences in the 2.5 seconds each episode gets to run, and it's using those to refine its distribution over models. So Mark used a Gaussian process for this, so it's easy to get a distribution of models out of a Gaussian process. Now Mark is just showing off. Okay, so that's like 1 or 2 orders of magnitude faster than you would get with a sample-free algorithm. That's what. It's ridiculously fast. It's the fastest known thing for that task, which is great. But it used a Gaussian process, and one of the things that we sort of struggle with is scaling these things up. And so people have started to use deep nets for learning models. So there was a paper out from Google DeepMind this year, I think, looking at learning deep models where you take a bunch of input observations, you stack some previous observed frames, then you have what is called a one-hot encoding of an input action, and you use a convolutional net to predict an observation and a reward. So using deep learning to learn a model of how the world works directly from sensory motor data. And again, this architecture is quite complicated. So this deep net predicts a one-step action, and it goes inside a thing which produces many steps. And actually, it doesn't predict the whole screen. It predicts a compressed version of the screen, which is learned using a deep net. And then that's used to produce rollouts, like whole sample executions. And it was used to attack a game called Sokoban. So what happens in Sokoban is that there's a dude, this kind of green thing, and then there are boxes which you can push, and you want to push them onto squares. But you can only push them, you can't pull them. And so if you push them into a corner, then you're dead, because you can't retrieve them. Okay, so this is the kind of thing you need planning for. You can't learn this because every small mistake that you make, just it's the end of the game, right? And a mistake that you make early on may have consequences much later on. So let's see this game. So what you see here is you see a collection of forward-played trajectories, and they're kind of highlighting one of them. These are imagined. These are kind of generated by the model that the agent has in its head, and it uses them to do planning. It uses them to look ahead and figure out what should happen next. And this is like 3 months ago, I think, super recently. Got all the boxes on all the little holes, right? No mistakes. So what you see in that case is that you see that a learner with a model does much better than a learner without a model. Okay, and you see that the further ahead you can look, the better your performance is. So this blue line over here is how well you do if you can look one step ahead. And the green line is 3 steps ahead, and the red line is 5 steps ahead. So you get like a diminishing return, right? It's only really useful looking 5 steps ahead, but it gets you some advantage. Okay, so we've talked about 3 different ways that you can do function approximation. And we've talked about how you might use them with a deep net, which is basically saying we're going to import all of the most exciting sort of new technology of how to do function approximation, how to do machine learning into reinforcement learning. Okay. Now, I think I have like on the order of half an hour left. Is that right? Oh, sorry, do you have a question? Yeah. Yes. In Sokoban? Yes. Mm-hmm. Yep. So the answer is kind of it depends. There are some domains in which learning a model is very effective, and there's some domains like the robot soccer example where it's not going to get you what you want, so it's not going to be accurate enough. So the state of the art is a hard question to answer. I can usually say what the state of the art is for one problem, but there isn't a single reinforcement learning algorithm that dominates anyone. I can say that at the moment, deep net-based RL algorithms, however you are learning, are able to solve the most interesting problems by far. They do take millions of frames, like it's huge amounts of data to solve them, but however you are using a deep net, those are the most advanced things we have at the moment. Yes. 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 Stochasticity, yes. In the video that I showed you, those are sampled transitions. So it's pulling a sample from the stochastic transition. In the actual game, it's not stochastic. But when it's doing learning, there's some stochasticity which affects the uncertainty of the agent. But it's also not a matrix, right? So this thing is a screen of pixels, right? And so it's learning from a screen of pixels plus an action to a new screen of pixels. So it would be a very large matrix, but it could be, in principle, it's finite, and you could make a matrix out of it. Yes? Mm-hmm. So people have done that. Usually what they do is they transfer the early layers. So you learn like visual features from all the games, and then the later layers are kind of optimized per game. But it's an open question, and it's kind of hard to answer because we don't completely understand what exactly all these things mean just yet. Yes, as far as I know, there isn't. I might be wrong because I don't think about that specifically. But as far as I know, there isn't anything where you could take chess and play Go using the same deep net because the input features actual input space might differ, and so that changes everything. Right? Yes. Oh. So I don't know a ton about that. I know there have been some attempts where you're taking some sort of nervous signal from the person's scalp, or maybe even from their spinal cord, and you're trying to map it to where they would like to move. And you do that by a sort of reinforcement learning thing where they tell you how good it was. I don't know much else beyond that. I just know that it has been applied a little bit, but there's a bit, there's complicated things in prosthetics, right? There's a bunch of design problems that have to do with the actual machinery and what you can and cannot sense. So I think it's a very big, very wide area and a lot of stuff going on. If that makes sense. Yes. How much do you want to pay for that robot? If you're willing to pay a couple $100,000 and have that robot only do that one thing, like 5 years. If you want a robot that you can say, hey, let me show you how to make my bed and also breakfast, and you want to pay $50,000, then 20. So it's a standard AI thing, right? We can solve, if we concentrate really hard, we can solve one problem very expensively. If we want to be general, then it just gets exponentially harder. No. Probably not in my lifetime, I would expect. Yes? Hmm. Hmm. I mean, in some sense, all of AI is neurologically inspired, right? But typically what happens is we make a bad cartoon. And so we say, okay, things are kind of like this. And then we stop talking to neurophysiologists and we run off. And there's a reason that we do that, and that's because humans have a whole bunch of weirdnesses, and they do some strange stuff. And, neurons are neurons because once we were fishes, right? So it's not clear that you want to necessarily emulate every last detail. Now, if you want to emulate every last detail, then you're sort of living in cognitive science land, which is great, and a lot of really cool research happens there. But it's not the sort of normal machine learning thing. There have been some things in the other direction. For example, that TD error that we've all been talking about. There is some evidence that dopamine is representing that TD error in the brain, that a specific neurotransmitter is representing that specific error term. There's a mountain of evidence now that is happening. There was a paper in Science in like 1999 or 2001 from Wolfram Schultz showing that dopamine reacts exactly the way that exactly mapping to the TD error. And that was one of the first times where something developed just as an optimization algorithm in AI actually showed up in the brain. It's a really big deal. And so it's probably the biggest thing in theoretical neuroscience at the moment is trying to understand exactly how that mapping works and what space you're learning and all that sort of stuff. So that's a case of we actually gave something back that one time. Cool. Okay, so 20 minutes roughly, is that right? Where's Benji? Or someone who's keeping time? Because we started about 15 minutes late. Would you want me to wrap up early? I have some other videos, but go ahead. Okay, cool, all right. My thing's died. Okay, so let me talk about my main own personal thing of interest, because now they've surrendered the mic to me, and that was a mistake. But so hierarchical reinforcement learning. So humans are much more like this than they are like an agent playing a sort of joystick, right? Humans are not simple agents. They don't do one thing. They don't learn to play one computer game or 50 computer games. They learn to do like almost an infinite amount of things. And so one question is, how do you manage all of that? If each one of those things is a reinforcement learning problem, how do you manage that you've learned all these reinforcement learning problems, and which one do you choose to execute next? Okay, and also, how do we manage the complexity of the behavior of generating something like human behavior from a robot? You know, when we decide where to go for lunch, we sort of actually think at quite a high level. We don't think about all the footsteps that we would have to execute and all the muscle twitches that we would have to execute and the gigabytes of data that we would see to go from here to lemons and zesty lemons down the road, right? Instead, we think, well, that's about a 10-minute walk, and I feel like that, and it's only 10 Rand or whatever, so I'm going to do it. That's a tiny abstract piece of information, right? That's nothing at all like what you actually have to do to execute the thing. So how do we kind of go one step beyond reinforcement learning for a single problem and think about reinforcement learning as an organizing kind of principle for how robots work? And so the way that we do this is we think of reinforcement learning problems as subproblems. We say that behavior is modular and compositional. And what that means is that almost everything that you do today is something that you did yesterday, just chopped up and reordered. Okay? And so the intuition here is just like a subroutine when you're programming, one way to think about the complexity of behavior is to say we do reinforcement learning, we learn a policy, and then we give it a name and we shove it in a library and we don't think about it again. It's just a thing that we call when we need it. And so there's a field called hierarchical reinforcement learning that thinks about hierarchies of reinforcement learning problems. And so the way that this works roughly is imagine that you've got your agent and you want to solve some reinforcement learning problem, and you're kind of cruising around trying to solve it, and let's say you hit a state where something in your brain tells you that that was an interesting little subproblem that you solved. It was interesting getting to this door. This door has a special property. Maybe I would like to do that again. Right? So here it's building a little graph and saying there's a min cut that breaks these things up in an interesting way. What you can do is create a second copy of that problem, change the goal from where it was to where you would like it to be, and learn to solve that problem as its own reinforcement learning problem. We call that thing a skill or an option. Okay? And then we give it to the agent as just a thing it can decide to do. It can just say, hey, go to the door. So now it can go up, down, left, or right, or it can go to the door. And so to sort of formalize this, one reinforcement learning framework that we use to do this is called the options framework, and it says that an option is a formal model of a little reinforcement learning problem. Okay, it has three things. It has an initiation set, which is the set of places from which you can execute your little thing that you've learned. It has a termination condition, which tells you when you're done. And then it has a policy, which tells you what thing to execute while you're running it. Okay, so this policy is the output of normal reinforcement learning. And this is just when you can run that little component and when to stop it. But given an MDP, we replace A, the set of actions, with O, the set of options, where each of those options has that structure. It's a little sub-policy in the MDP. You can run it when it's in its initiation set. It runs for some amount of time, it gets to a termination condition, and then it's done. And there's a bunch of questions associated with this, like how do we characterize the resulting problem? How do we plan using options? How do we learn using options? How do we characterize the resulting policies? And it's actually pretty easy, right? Everything comes from the Bellman equation, right? So if you write down the estimated TD error and you think about an execution that can run multiple steps, the only way that it changes is that occasionally you get this T in the power of gamma. right? It used to be gamma to the 1. Now it's gamma to the number of time steps that you took to execute something. And the reward is also a function of the number of time steps. So if I had a skill like go for lunch, and it took 15 minutes, and it cost me minus 100 reward to go there, then I would have gamma to the power of 15, if we're measuring in minutes, and the reward function would include that amount of time in it. And all your previous planning algorithms and learning algorithms just work the same way. Everything's very easy. You just need to put that T power in there. So what does that look like when you plan? You might have a little grid world problem like this, and you would give it a skill like this. So here we've got a hallway problem, and we've decided to give the agent a skill to move from anywhere in that room to that doorway. Okay, so we've got a little option defined like that. And learning that used to look like this, if you did one TD backup from a state, you kind of slowly would, your policy would be sensible, one block out and 2 blocks out, 3 blocks out. When you have these options, this is 1 block out, right? The option takes you all the way there. Does the whole big thing. And so learning propagates much faster. Planning propagates much faster. Because you've rewired this MDP so that instead of having to go a little bit at a time, you just jump all the way from where you were to all the way where you'd like to be. So why would you ever wish to do this? Well, one thing that it does is it rewires the MDP so that the connectivity of it, if you think of it as a graph where you can move from one state to another, used to be kind of limited. Now it's much more global. Right? Now you can kind of jump. By making one decision, you can jump from one state to a whole bunch of different states very quickly. You can also use them for transfer, which someone asked about, and you can do skill-specific abstractions, which I think we'll skip because we don't have a ton of time. So what does rewiring look like? What rewiring looks like is instead of each of these edges being one step away from each other, we've said that this room is one step away from this room. And what we've done is we've changed the diameter of the problem. We've changed the number of successive correct choices you have to make in order to solve it. Okay, so if you think about how many correct footsteps I would have to make in order to be able to get from here to lunch, it's hundreds or thousands. But if I have an option that says, walk in that direction until you see the road, then go left and then go right, I have to make one correct decision. Okay, and dimension and the sort of diameter of a problem is a dominating cost in reinforcement learning. The other thing that it can do is transfer, which is to say that subtasks recur. So you may go for lunch many times, and it may have been expensive to learn to find that particular tuck shop the first time you went there. But if you can cache that solution, then many, many days in the future, you don't need to relearn that subtask again. Okay, you can just execute it whenever you need it just by calling it by its name. All right. So they're kind of a mechanism for transferring. If you have to solve many problems in the same MDP over and over and over again, you can find the subtasks that recur, and then that speeds up learning dramatically. So we can go from a learning curve that looks like this, if you only have primitive actions, to one that looks like this, if you have transferable actions, to one that learns like this, if you have exactly the right set of options. Right? There's basically no learning going on here. You pick a couple of things, you get the right solution, and you go home. This is an example of transfer where this is learning with no transferred options. This is learning with transferred options from one previous problem. This is 2 previous problems, 3 previous problems, 4 previous problems. And you see that you can retain information across the problems over and over and over again to make problem solving easier and easier. You're building up a vocabulary of pieces of the solution, and you just assemble the pieces again kind of at runtime. So let me show you a video of this happening, because we're running out of time. I'm going to show you a video of a robot learning to solve a task using reinforcement learning, and then we're going to take the solution to that task, and we're going to cut it up into options. We're going to save those options, we're going to give it to the robot, and we're going to ask it to solve a second task. No, it's automatic. There's an algorithm. I'm just not going to talk about it, but there's an algorithm that segments the trajectory into options. Yes, it's a change point detection algorithm. Okay, so here's a robot doing reinforcement learning. What it can do is it can go up to things on the wall and it can stick its hand out and move it left or right or up or down. It can lean forward or it can lean back. And it can move between special locations that I've marked out for it. And what it's doing is it's learning slowly over time that this button controls a switch that unlocks this door. And that if you've unlocked it, which means you have to go up to the button, you've got to stick out your hand, you've got to lean forward, you've got to go back, you've got to retract your hand. If you do all of that an odd number of times, and then you pull this lever, the door opens, and you can go and push the switch and escape. Right, so this is the optimal solution to that problem. You can see the learning up in the right corner. You can see what the robot is seeing over here. And the thing is that it's a hard learning problem because it sequences a bunch of little small things. You've got to go up to the thing, you've got to stick out your hand, you've got to lean forward, you've got to go back, you've got to retract, you've got to turn around, you've got to go to the pink thing, you've got to stick out your hand, you've got to go down, you've got to go up, you've got to retract. And that's what makes reinforcement learning hard, right? It's this diameter of the problem, how many successive action executions you have to get right. But you can do it, right? So this took 5 or 6 episodes to learn, which is like a couple hours of robot time, which is sort of long and a bit boring to watch. But the point is that you can kind of learn a solution by doing reinforcement learning, and maybe it was hard the first time, but then you can take that solution, right? This trajectory that the robot is just executing. You can take that solution. Okay, so now it gets to go home because it escaped the room. You can take that solution and you can break it up into sub-skills. Sub-skills like pushing the button. Okay. Or pulling the lever. Now, these were all things the robot could do. It just had to sequence a bunch of things to do them. And now what it's done is it's learned a low-level motor policy that just does them in one decision. Pull the lever, press the button, push the green switch. Then, if we put that robot in a second room and we ask it to solve the problem, what does it do? It learns, if we don't give it these new skills, it's just sequencing a large number of these tiny little motor actions, one after the other, over and over again. So when it comes up to something like this handle, what does it do? It does exploration. It sticks its hand out, it moves it left, it moves it right, it moves it up, it moves it down. And it might even decide to go away. Right? There's no reason it sticks around, other than we just got lucky here. Eventually it figured out what to do. But it's learning at the level of these tiny little motor primitives. But if you give it the motor skill and it walks up to the handle, it knows how to deal with handles, it just pulls them. It's one decision. So if we put that in a second room, on the left is without acquired skills, on the right is with acquired skills. You'll find that if you watch the two of them separately, the one on the left is doing little optimizations about all the things that it could do, and the one on the right goes up to buttons and pushes them and handles and pulls them. If the one on the right is learning at a much higher level than the one on the left. And why has it done that? Because it's learned some procedural knowledge, it's taken this procedural knowledge, and it's used it to become better at learning. Therefore, it is able to solve this problem much faster than it would be able to otherwise. So we can do things more quickly. So that is how you manage the tiny pieces of information that you learn when you solve little MDPs. You break out pieces of them, you accumulate procedural knowledge, you get better and better at doing stuff by accumulating sets of things that you already know how to do. Okay. Yes? Oh, those are AR tags. They just simplify vision. Because I'm not a vision researcher, so I cheated by labeling the spot on the wall that the robot's supposed to go to with big tags that it can see from far away. So when it had like 3 things it could go to, it could kind of see them visually, and then it could kind of follow the direction towards the tag. So actually that brings up an important question, because we say, we can look at that data and say, are we done now? Is it finished, right? Is that all the thing you'd need to be able to do to generate intelligent behavior, right? We just accumulate more and more of these things, and then we can go home. And the answer is no, because we're missing a component, right? If you had this sort of simple problem of a robot moving to a key, it had options to move to a key, and to move to a lock, and to pick up a key, and you asked it to learn to unlock the lock, that's a very easy problem, right? It's just 3 actions in sequence, and it's a small state space, it's not a big deal. And now what happens if we increase the size of the room? Should this problem get any harder? And the answer is, if you have these options, it should not get any harder, right? You just go there and you do the thing, and then you go pick up the key, and then you put the key in the lock. And if we make this toy thing a real robot with a big sensory motor space, should the problem get any harder? And the answer is no, the problem should not get any harder. Even if you have this huge sensory motor space, there is an abstract representation which says, is the robot standing on top of the key? Has it picked up the key? Is it standing in front of the lock? Which is sufficient to describe the problem in all three cases, no matter how complicated the original state space was. And that only happens because you have those options. Those options induce the ability to use an abstract representation. So what I'm going to show you in the next 5 minutes, and then I'm going to let you go, I'm going to skip all the math, because videos are cooler than math, is a domain. So my group has been working on this problem of learning these minimally abstract representations once you've got the motor skills. So here's a little room that we built. It has a cupboard and a cooler. The cupboard and the cooler, the robot can move between those two places, and it can open and close the cupboard and the cooler when it's not holding anything. And there's also a light switch. When the robot turns the light switch on or off, it changes the status of a light inside the cupboard. If the light's really bright, then it can't actually see anything inside the cupboard, and it can't manipulate stuff in the cupboard. But when you open this cupboard, it actually hides the switch, right? It blocks the access to the switch. Now, I've just given you a very abstract description of this problem, right? You could write down like a 30 or 40 state MDP very quickly, given what I've told you, right? But that's not what the robot gets. The robot gets this. The robot gets high-dimensional sensory motor data. And we'd like to be able to recover that abstract representation of the problem by just examining the properties of the skills that the robot has. So we built a bunch of theory, which I've skipped over, and we did some learning. So here is the robot executing these motor skills over and over again, and what it's observing is it's observing big point cloud. Okay, it's an HD point cloud, so it's a couple of megs. Which of my motor skills can I execute? And then for each motor skill that it chooses to execute, big point cloud, execution of the action, big point cloud. That's the data that it gets. See there, it's too bright. It can't pick up that object when the light's on, but it can pick it up when the light's not on. It can't open the cooler when it's got something in its hand, because it needs both hands to open the cooler. There's a bunch of logical restrictions, right, that are easy for you and me to describe, but not in the sensory motor space of the robot. They're hallucinated, they're imagined, they are not in the world. They are things that we have added to the world to make planning easier when we think about it. But it turns out that you can learn them. So let me show you a couple of learned such abstract representations. This is one describing what happens when you execute the navigate to cooler action. So it says that symbol 1 has to be true for you to be able to navigate to the cooler. And afterwards, symbol 1 is no longer true and symbol 0 is true. And each of these symbols is actually a name for a distribution over sensory motor data, a probabilistic distribution. This distribution happens to name only things to do with the robot's location in the map. Okay, so symbol 0, these are samples drawn from that distribution. And that shows you that the robot is standing there, which is where the cooler happens to be. And symbol 1 is then the robot is standing there. That's where the cupboard happens to be. Now, you and I can see the robot is at the cupboard or the robot is at the cooler. That's easy to understand. But in this case, the robot has identified that distinction on its own. It's learned what being at the cooler means and being at the cupboard means, the symbol 1 and symbol 0. They're automatically generated. And it's learned a rule for which of those has to be true for you to be able to execute a skill and which has to be false. So that's an easy one. Let's look at a more interesting one. This is what it means to be able to open the cupboard. Okay, so symbol 1 has to be true. You have to be standing in front of the cupboard. Symbol 3 has to be true. That's a distribution over the robot's joints. I don't know if you notice when it picks something up, it holds it up here. So the robot's looking like that means it's not holding something. And then symbol 4 has to be true. That is a distribution over pixels in the grid around the cupboard. Okay, so if you look at that distribution, I'm drawing samples from it. The switch might be on or off, and there's a bunch of noise and compression artifacts, but this says that the cupboard has to be closed. And then when you execute open the cupboard is no longer closed, and now you get this distribution. There's a couple things to note about it. The switch could be on or off, or there could be an object in there, or there might not be, and there's a bunch of noise and other stuff. But that says that if this whole operator here says that if you're standing in front of the cupboard and you're not holding something and the cupboard's closed, you can execute cupboard open, and afterwards the cupboard's no longer closed, it's open. Okay. This text file over here is sufficient to do planning with. It describes an MDP, describes a reinforcement learning problem, It's a complete model of that reinforcement learning problem, and you can plan with it. So it's literally a text file. So we've taken these gargantuan sensory motor HD images that we've been pulling, and we've distilled them down to a tiny little textual representation like that. And moreover, in the theory that I didn't show you, we can prove that it is exactly the correct one. Okay, that you have to have these symbolic representations and no other symbolic representations in order to be able to plan with your motor skills. So let me show you planning. Here the agent is going to move a bottle that's inside the cooler to the cupboard. Note a couple things. The cupboard and the cooler are both closed. The switch is on, so it can't touch anything inside the cupboard. Now I've asked it to do planning. It takes 4 milliseconds to make this plan. About approximately 2 of those milliseconds are reading it from disk. Okay. And here's the plan executed. Oh, why is this sound? Okay, so what it'll do is it'll open the cooler first, but then it won't pick up the object, because it knows that it needs to have the cupboard open in order to be able to put the object down. And it can't open the cupboard if it's got the object in its hand. Moreover, it knows that if it opened the cupboard, it wouldn't be able to turn the switch. So first it turns the switch, then it opens the cupboard, then it goes back and gets the object. This is what classical planning classically does, right? Is that it sort of spots these kind of weird logical constraints, it goes and fixes them, and then it does the obvious thing, which is that it picks up the bottle and goes and drops it off. Okay, this planning was done with a learned symbolic representation completely from scratch by an agent that knows nothing about physics or that bottles should be inside cupboards or not, or any of that situation. It's learned it just by observing point cloud data, and it's able to use it to plan. I also asked it to clean up everything afterwards, so it's going to close the cupboard and the cooler and do all that sorts of stuff. It takes a little while because the merging of the point clouds at runtime is slow. That's not planning. It's just sensory motor processing. It's all done on a board. There we go. Cool. Okay, and you can form hierarchies out of these things. Talk to me in person if you want to know about that. So, just to close up, because everyone is hungry. So we've talked about reinforcement learning being like the whole AI problem, right? It's the whole thing. But it's incumbent upon us to take these very simple models and learning algorithms and make them real. If we're going to solve the AI problem, we need to actually go all the way, because brains are computers, but humans are robots. And so if you want to take that metaphor seriously, you need to take your agents seriously, and that means high-dimensional, complex inputs, complicated plans, and dealing with the real thing. Okay? Thank you. Yes.